All right, so today's lesson is about linear programming. So linear programming is basically a type of math where we use systems of linear inequalities to find what we call an optimal solution. So the optimal solution will either represent a maximum, for example, if you want to find out what the maximum revenue would be, or it would be a minimum. So for example, if we want to find the minimal costs of production. So first of all, an optimization problem is a problem where a solution needs to be found to maximize or minimize a quantity, such as revenue cost, that follows a set of conditions about that problem. Now that set of conditions are known as the constraints. And so the constraints, all right, are going to be represented as linear inequalities. So right off the bat, you should be pretty much expecting that we're going to be hanging out in quadrant number 1. So x greater than or equal to 0, y greater than or equal to 0 will be always in play. So the region where our solutions exist are called the feasible region. Okay, so that's going to be the overlap area, but we're now calling it the feasible region. And this region is going to be some kind of shape. As you've noticed, the shape of the shaded area of 2 or more inequalities, we call this the feasible region. So because we're looking for an optimal answer, we're not going to be looking in between, like inside that feasible region. We're going to be looking at the edges, and specifically, we're looking at points, okay, x, y coordinates. So we'll be looking for the so-called corner points. All right, so the corner points are going to represent our possible optimal solutions for our problem. Again, the x, y coordinates. All right, so now, what do we do with those x and y coordinates when we find them? We are going to be creating an objective function. So an objective function, very important, is represented by an equation. And that's going to be given implicitly in the problem. So we'll have to build it, all right? But it's going to be giving information about either finding the maximum revenue, or the minimal cost of production. So you will be able to find it, and it is going to be a linear equation. The constraints involve maximum and minimum conditions about our objects, as well as any comparisons between them. So we'll begin. Color here. All right. So here's an example. A vehicle manufacturing plant makes both cars and SUVs. In one day, they can make no more than 25 cars or 20 SUVs. The plant can make between 30 and 40 vehicles in one day. The plant makes a profit of $3,500 per car and $2,500 per SUV. So this here is going to be our hint, okay, for the objective functions. I'm just going to put this in red. Determine the combination of cars and SUVs that will maximize their profit. So we're dealing with cars being produced, and we're dealing with SUVs. So again, we're only doing 2 variable inequalities, okay? So a tricky thing that students find is determining, like, what do the variables represent? So we're talking about manufacturing cars, so X will be the number of cars, and manufacturing SUVs, which will be represented by Y. Now, because we're looking for a profit in our objective function, capital P will represent our profit. And I think let's just deal with the objective function right away, so you can see how we will build this. Our profit P comes from $3,500 per car and $2,500 per SUV. So if cars are X and $3,500 per car, it would be $3,500 times X plus $2,500 times Y. So that would be our objective function that we will be looking to find, okay, the maximum profit. And our X and Y coordinate is going to come from this feasible region. Okay, so that's sort of important there. All right, so we'll start with the objective function. We got that out of the way. So I've put this together for you in a list, all right? And I would suggest you work on a list and you start, okay, going through it logically. So the first things we have to realize is that we are going to hang out in quadrant 1, right? We're not going to have negative cars. We're not going to have negative SUVs being made. So X and Y both must be greater than 0 because you cannot have less than 0 cars and 0 SUVs. So that's our quadrant 1, okay, constraint. Now, first thing it says, in one day, they can make no more than 25 cars. So clearly 25 would be the maximum number of cars that they could make. So X, being the number of cars, must be less than or equal to 25. So that would represent our maximum value for X. Likewise, it says that 20 SUVs can be made per day, no more than 20 SUVs. So that means Y, the number of SUVs, must be less than or equal to 20. Okay, so now you can see that X must be between 0 and 25, and Y must be between 0 and 20. All right. Then on to the next part. The plant can make between 30 and 40 vehicles in one day. So that's going to be a minimum amount of total vehicles made and a maximum amount of total vehicles made. So if we're making cars and SUVs, the X plus Y would have to be greater than or equal to 30, okay, because they can make at least 30 vehicles total. And likewise, they can make no more than 40, so X plus Y must be less than or equal to 40. All right, so we have 1, 2, 3, 4, 5, 6. All right, we have 6 inequalities that we are going to put in here. All right, so we are going to go into Desmos and we are going to start the graph. Now, again, we're not going to put X and Y greater than 0. That's going to be our constraint that we're going to put into the row using our set notation, as you saw in a previous lesson. So let's begin with, okay, the number of maximum X. So X must be between 0, okay, and 25. So 0, oops, not O, 0 has to be less than or equal to X, but X has to be less than 25. So you can see how we kind of, if I just zoom out here, there we go. That's the maximum amount of X, maximum amount of cars between 0 and 25. Likewise, we can do the same thing for the SUVs. So 0 must be less than or equal to Y. Y must be less than or equal to 20, I believe, if I remember correctly. Yes, 20. All right. So now we have X plus Y must be greater than or equal to 30. Okay. And X plus Y must be less than or equal to 40. Okay. And so again, in our gear wheel, we will make all the same color. Okay. And so what we can see here is a feasible region bounded by this. Okay, so we have the overlap being right here. Now again, another thing we could do is get rid of that. Okay, and we could put in our restriction with our set notation. X, sorry, 0 must be greater than or equal to X. Whoops, back up here. X must be less than or equal to 25. And we'll do one more. The Y, 0 must be less than or equal to Y, which must be less than or equal to 20. Now we've cut that off. Liking this? I don't think it's liking this. Okay, it does. Actually, get rid of all that. There we go. Okay, so my apologies there. We can add in the, just as a recap, in case you're wondering what I just did there, these individual inequalities, we can tack on to the two variable inequalities. Okay, so now it just kind of makes our graph look a bit better. But now that I'm thinking, it's going to probably make it tricky, okay, to see the endpoints. So actually, after all of that, I'm going to delete everything here. Okay. All right. So x plus y must be greater than or equal to 30. X plus y must be less than or equal to 40. And I'm working backwards, so just bear with me here. We'll do the original. 0 must be less than or equal to x, which must be greater than or equal to 25. Yeah, we'll do it that way. And 0 less than or equal to y, less than or equal to 20. Okay, my apologies there. It is a Monday. Okay, so here we can see our feasible region, right? So that's what we want. So these are the 4 points we're going to be looking for. Okay, so you can see this trapezoid here. That represents the feasible region, and that's what we want. These are the 4 corner points. So if you remember, to get this graph, we're going to snip. Please catch all the graph. There it is. Notice X and Y aren't labeled. We should label them. Okay, so actually we'll go back here and oops, snip. Okay, go here. X is the number of cars produced daily, and Y is the number of SUVs produced daily. All right, and now we'll go ahead and snip this. Perfect, we caught everything there. Copy, and we can close that. And we'll go here to our graph, paste it in, doesn't need to be that big. All right, and what you should do is catch the corner points. So I did not do that. So I'm gonna go back, click, 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 and click. Those are we want those 4 points. So now we'll snip. And we have it. Good, see the points are there. So now we've got our points. Make this a bit smaller so it's on one page. There we go. So those are the points we want: 1020, 2020, 2515, and 255. So here we have the objective function stated, and you notice that we've got 1020. There's the first point. We've got 2020. We got 2515, 2515, and we've got 25.5. So what we simply do is we take the x value, plug it in, times it by 3500, take the y value, plug it in, times it by 2500, and add them. So we're going to add we're going to do all 4 objective functions. And what we get here is, because we're looking for the largest maximum profit, all right, we want to find the maximum profit. $125,000 per day represents producing 25 cars and 15 SUVs. So the final answer would be, based on their objective function, the plant should manufacture 25 cars and 15 SUVs to maximize their profit. So what I have for you here to practice is, without a context, just to get you comfortable with this linear optimization, I've given you the constraints, okay? So those go into Desmos, you graph it, you get your feasible region, click on the corner points, and then I'd like you to find the minimum optimal answer, okay? So I'd like you to do that here. This would be practice number 2. And then for number 3, this is number 2, but this technically should be number 3. You can try one for context, and I will upload the answers on another video for tomorrow. I'd also draw your attention to practice homework in your textbook. All right, do those questions there. And if you have any other questions, don't hesitate to email me. And thank you for listening, and apologize for the choppiness of this video on a Monday.